Time for synthesis. As I mentioned in the previous video, now we're going to look at different ways of efficiently making primary, secondary, or tertiary amines. And we're going to start with the Gabriel synthesis. Now here's the full view of how this reaction works out. We use a very specific molecule. This is called phthalimide, and because of the fact that the nitrogen is technically sandwiched by two carbonyls, makes this NH bond pretty acidic. Acidic enough that you can efficiently deprotonate it with hydroxide and then use that as a nucleophile to attack alkyl halides. And because the nitrogen is already coupled to two other carbons, then here you have only a single alkylation. And even though you do have that lone pair of nitrogen, the reason additional alkylations do not take place is because that nitrogen is engaged in full-on resonance with the carbonyl bonds that are adjacent to it. So that nitrogen is very inaccessible, at least from the point of view of acid-base chemistry. All right, so what basically happens here is that Gabriel just says, okay, well, yes, it looks like a funky amide, but it's still an amide nonetheless. So you can treat this with hydronium and heat to liberate your amine component out of this thing. So you end up making the carboxylic acid derivative, phthalic acid, and you end up producing the ammonium salt initially. And then after that, you could do base workup to remove the proton and yield the neutral amine if that's what you're after. So let me show you how this works out. Now, obviously, since the lone pair of nitrogen is inaccessible for additional nucleophilic reactions, this is a good strategy for making primary amines, as long as the SN2 reaction that happens early on is done with good SN2 substrates. All right, so let me show you how the whole mechanism of this thing works out. So first, as I mentioned, you have to deprotonate phthalimide with hydroxide. So you simply attack the NH bonds, the electrons move over to nitrogen, and now you have, in this case, the potassium salt. It could be sodium, it could be lithium. That depends on the cation that's being used, along with the base. So we have potassium phthalimide that's very much ready to attack any good SN2 substrate. So here's where you introduce now, um, in this case, methyl bromide. Any other good SN2 substrate will do the trick as well. So you attack your carbon, you break that carbon halogen bond, and now you have created a methylated nitrogen derivative of phthalimide. Okay, so now what you do is now you start removing that nitrogen, and technically speaking, this is chemistry that we have talked about under the carboxylic acid derivatives chapter of this lecture series. But just to kind of refresh you on how that works out, I'm going to show you the mechanism here anyway, even though technically it's material that we've covered in the past. So first things first, you protonate one of the carbonyls of phthalimide. The electrons move over back to oxygen, creating water in the process. And of course, the protonated version, the protonated amide derivative, right? All right, so that carbonyl carbon is now activated for nucleophilic attack. And the water that you have around, or even the water that you just generated, can now attack that carbonyl carbon, and the electrons of the pi electrons of that carbonyl bond basically move over to the oxygen to give you a neutral product, at least from the point of view of what you had before, right? Because the water that came in, now that develops a positive charge. So what happens next is that you have to basically shuffle this additional proton. You take it away from water and you dump it onto the adjacent nitrogen, that has a lone pair. Now, typically this is done with a solvent, but just to save you a little bit of time, I'm going to do the unthinkable and have this thing happen from functional group to proton directly. But in reality, solvents coming in, removing this proton, and then dunking it onto the nitrogen. All right, so we'll do this intramolecular reaction just for the sake of space and time. And what this will do is it will now give you a cationic amine component, or a protonated amide if we want to be technical. So what takes place now is that the oxygens that are adjacent to it with their own lone pairs, right? They can come back down and reform the carbonyl bonds that was there before. But in order for this to happen, you now have to break the carbon-nitrogen bond. And the reason that's the bond that's being broken is because now we have that as a living group, a good living group at that, right? So this bond breaks over so that you have now the lone pair on the nitrogen. But in essence, what you've done is you've broken that second ring. Now you have a protonated carboxylic acid and you have your amide. So here we do have more proton shuffle that happens, and because of the positions, I'm just going to go ahead and use solvents for this because it'll be a little bit silly to to try to do the deprotonation protonation, happen within the same molecule without the assistance of solvent. So the water is going to attack that proton, basically remove it from your carbonyl. The electrons move over back to oxygen, making that a neutral carboxylic acid moiety. And now that hydronium that has been generated simply, moves about and now interacts with the carbonyl of the amide segment. So that carbonyl attacks the hydrogen, the electrons go back to oxygen, and now you have protonated amide, which is the same thing as saying that you have now activated the carbonyl carbon of the amide for nucleophilic attack. So that's where a second water molecule comes in, attacks the carbonyl carbon, the electrons go back to oxygen, and you now have this intermediate with an oxonium cation. So we do a little bit more of proton shuffle, and here once again I'll do it intramolecularly from nitrogen directly to the proton, but as I said earlier, the solvent is actually involved in this process. So we're just going to do the quick removal of proton. Now it's going to get dunked on nitrogen, and when this happens, you have now created an amine leaving group. And because of all your adjacent oxygens, you can re-establish the carbonyl bond that you had before at the expense of that carbon-nitrogen bond. So you basically break that carbon-nitrogen bond altogether, and this ultimately has the effect of leaving you with protonated phthalic acid and methylamine. Now, needless to say, this is a pretty strong acid. So the amine really has no choice here. The amine is going to get protonated. Um, so this last event of attack of that proton, the electrons going back to oxygen is happening guaranteed. Yes, there's no much choice for that nitrogen. But the end result is that you end up with phthalic acid, the byproduct, and you have methyl ammonium salt. So typically when you do this in the lab, what you would then do here is after you separate phthalic acid from your actual methyl ammonium salt, right? Phthalic acid will be soluble in organic solvent. The methyl ammonium cation will be dissolved in water, so you can separate it that way. And after that, you can then treat your water with base in the presence of ether solvent that will deprotonate ammonium, bring it back to amine, and you can extract it with your organic solvent at that point. So it's not too difficult, but just so you know, many of these small molecule amine compounds are very foully smelling compounds. So if you are to do things like that, then you better have a good fume hood to do this. Okay, so that's the first type of synthesis. In the next video, I'm going to show you two additional syntheses. I'm going to show you the A side reduction and the nitrile reduction. So I'll catch you on those videos. Bye bye.